So thank you very much for this nice introduction, Michael. So I'm indeed Anik de Groof. I'm working for Solar Orbiter as a science operations scientist. I'm one of the people coordinating the instrument operations on board. And so today I would like to take you into the history of 50 years of solar observations from space, and also, of course, all the exciting things that are happening today. Okay, so the sun, we can really call the sun our star, actually, just because the sun is for us so important. It's really the star that gives light and energy and thus life on Earth. On the other hand, if you look at it just from the star point of view, it's a very ordinary star. It's not particularly big or small. It's not particularly old or young. But of course, it's much closer to us than any other, and that makes it so special for Earth. On the right here, I've added a few facts. So it's the star is currently about 4.5 billion years old, and we expect it will live for another 4.5, 5 billion years roughly. It is at a distance at about 150 million kilometers away from the Earth. It has a diameter which is more than 100 times the Earth's diameter, and it weighs more than 300,000 times more than the Earth. So, as the other planets, Earth is rotating around the star, so we are all part of the same solar system. Now, because the sun is so important for us, humans have, of course, always been very fascinated about the sun. We wanted to get to know our star and how it's affecting us. And this goes back until the very early days, of course. And originally, the sun was mainly observed from Earth for religious reasons, worshipping it as a god more. But let me jump directly to the time where we started to look at the star more from a scientific point of view. So it has been observed in ancient times as well. And then, of course, that happened by naked eye. Well, hopefully with some filtering to not burn the eyes. But so even already in those days, people knew that the sun was not just this bright ball in the sky, but there were some interesting features on it. So they could already, by naked eye, see that there were some dark patches. So the existence of sunspots was already known. Now, they were not really systematic studies until they invented the telescope, because only then they had enough resolution to actually really see the sunspots in a bit more detail and to start making drawings of them. And Galileo Galilei, who invented the telescope, was one of the first ones making drawings like the one you see here on the right. And also his colleague Scheiner in Germany made similar drawings, like the one you see here in his catalog Rosa Ursina in 1630, where he was also following a sunspot group when it was rotating over the disk. So also at that time, they saw already the solar rotation, so the sun rotating around its own axis. Now, it took quite much longer until the 1840s that somebody really took the effort to make daily drawings and to make them very, very systematically. And that was Schwabe, also from Germany, who was actually looking for a planet that was closer to the sun than Mercury. And to find that planet, he was making daily drawings. And it's only because of his work that we discovered that the number of sunspots were varying with the regular period. So there were times, or rather years, where there were not many sunspots at all, and then other years where there were much more. So he found this periodicity, and Wolf later confirmed that there is an 11 years sunspot cycle. So since those early days, actually people have been counting sunspots, on our star, and try to find indeed these regular patterns. So you see here from the 1700s, you see the so-called sunspot number. It is a particular way of counting sunspots and groups. So you do not count them all one by one. Some of them count for more if they show up as a group. But so you see here this sunspot number going up and down, indeed, with this periodicity of roughly 11 years. But not all the solar cycles are equal. So you have years or cycles where there are much more sunspot activity than at other years. For example, this period here we call an activity minimum, because over more than 20 years there were clearly much less sunspots than normal. So this goes up to today, and so you see that we are currently in what we call a solar minimum, not many sunspots on the sun, and not much activity. So we still do solar observations from Earth, of course, and we still do it in what we call visible light, which means without any particular filter. Now, telescopes have become better, we have better cameras, and so in the end, we also get much nicer images with better resolution. So here you see some recent images of the sun with some dark sunspots in a group. And you also see, if you take movies, you see actually a lot of structure in such a sunspot. And so we have given several names to all these different features. So you see that also the area around it is not just uniform, but you see those cells, active cells, where hot material is bubbling up. And then you see the core of the sunspot, which we call the umbra, and an interesting region around it we call the penumbra. So this layer of the sun that we see in visible light, we call the photosphere. And that comes from the name photo, which means light, because most of the light that the sun emits comes from this layer. And in the meantime, we have found out that that layer is at about a temperature of 5,000 degrees. And I will tell you more later how we found that out. So what happened in the meantime? Going back to the 1800s, in the meantime, we got more knowledge about the sun because more and more people started looking through their telescopes every day and observing those sunspots. Now, Carrington in the UK at some point was really lucky. On the 1st of September 1859, he was looking at a very interesting sunspot group, quite a complex one, and then suddenly he saw those bright flashes. He drew them, and he first saw them here in the areas A and B, and then a few minutes later, suddenly the brightness was seen in these areas C and D. He tried to get some colleagues around him to actually also see the same that he was seeing, but the whole event only took several minutes. So this is what we now call a solar flare. Carrington saw the very first solar flare happening while he was watching through his telescope. And so a flare is a sudden release of energy, but in the form of light, so in the form of radiation. Now, his sunspot drawings also revealed something else, namely that the sun is not rotating as one body at the same speed, but actually the sun is rotating faster at the equator than at the poles. And this is what we call differential rotation. And I will say more about that later. Then also in the 1800s, Fraunhofer was using another technique to analyze the sunlight. He was using spectroscopy. So in spectroscopy, you actually split the light coming from a particular source, like you see here, for example, through a prisma, to find out all the different wavelengths that are embedded in that light. And so what Fraunhofer did, he studied actually the light coming from the sun to find out about its chemical composition and also its temperature. So what he saw was that the sun was in general emitting light in the whole visible spectrum, but there were some interesting dark lines, which we now call absorption lines. And what these lines tell you is that there is some material in the way between the source and the viewer that is absorbing light at exactly this wavelength. So this kind of tells you what the material is, what the chemical composition is of the atmosphere of the sun, so the outer layers of the sun, because these are the ones that are blocking this light at these lines. So in this way, Fraunhofer found about the temperature of different layers in the sun, but also many new questions popped up. There were lines at different places where they could not really explain what element it was. There were lines that were split and so on. So now that we knew that the sun was emitting in many different types of light, you can also start filtering particular wavelengths. And so one of the wavelengths that is very popular to observe from Earth is H-alpha. So H-alpha is a type of light that's being emitted by hydrogen when the electron jumps from one energy level to another. And so the sun seems to emit a lot of H-alpha light in a particular layer that we call the chromosphere. And the chromosphere got its name from the name chromo, which means color. So it is a layer which is on top of the photosphere. In the photosphere, what we saw before, we often call the surface as well of the sun, although the sun doesn't really have a real surface. So this chromosphere is a little bit higher up, and it's a bit thicker than the chromosphere, and it's also at a higher temperature. And it has this nice color red. Now, in the chromosphere, we also found out about new features that we did not see before. For example, these arcs here of solar material that you see sticking out of the sun are solar prominences. And the same thing is actually this dark line you see here on the background of the chromosphere. So here it looks dark because it's slightly cooler than the background, but it's of course hotter than space here behind. So these are solar filaments or solar prominences, but it's the same thing in the end. We also saw kind of hairy-like things sticking out with a lot of activity and movement in them. These we call spicules. So with those two observations, these two observations we could take from Earth at regular times. We could take daily observations if we wanted. But there are also particular events on Earth where suddenly you see the sun in a completely different light. And that was quite mysterious in the early days. For example, during solar eclipses, the moon is shielding the bright light from the photosphere, and then something truly magical happens. Because in the end, most of the light emitted by the sun comes from this photosphere. So if you suddenly have something, in this case the moon, blocking that light, then you suddenly see what's happening in the outer layers of the sun, in the atmosphere around. And it turns out that the sun has a crown-like layer around it, which we call the corona. And so the corona stands for crown. Of course, these days we have more things called corona, but this particular one is the solar corona that I would like to focus on. And so it is the outer atmospheric layer of the sun, and it is extending far in the solar system. It's not confined to the sun, but it's actually continuously losing material into the solar system. And from spectroscopy, like Fraunhofer was doing, we also found out that the corona must be really hot. It's suddenly up to 1 to 5 million degrees in this outer layer, something which you would really not suspect, because in the end, the energy that is created by the sun comes from its core, from the internal part of the sun. So you would think that the temperature would go down if you move further away from that core. And this is indeed true up to the photosphere at 5,000 degrees. And then for some reason, it's getting hotter again. So this is one of the mysteries that we faced when we were still only looking from Earth. Now we are still observing eclipses from Earth, and this is a more recent picture. It's actually not just one picture, it's quite a processed image. So this is a composite of 29 eclipse images that have been really processed to get most out of it, to get most of the contrast out of the picture. And so here you see the moon shielding the photosphere, so the disk of the sun. You see part of the red chromosphere with the prominences sticking out, and then you see this beautiful corona sticking out of the sun. So, what now? Well, so we know already, okay, the sun has many different phases. We can observe some of those phases from the sun, but we also know that on Earth, you can't see all the types of colors that exist in radiation. So from analyzing the sun spectrum, we know that a corona must be very hot, but typically light that is emitted at very energetic wavelengths, so this means short wavelengths or high frequencies, is blocked by the atmosphere. And then I'm talking about ultraviolet light, of which only a little bit gets to ground. X-rays can't be seen from Earth, and gamma rays, for example. These are shorter wavelengths, very energetic radiation that could be emitted by the sun, but we can't see it. And then on the other side of the wavelength range, you have infrared, microwave, and radio. And only radio, again, you can observe from Earth. So if you want to learn more about the sun and about the different types of light it's emitting, there is only one way, and that is going into space. We have to escape this atmosphere, this layer of air, so that we can see much more and we can observe the sun in all its glory. So what if we go on a space mission out of the atmosphere and we take different cameras that are sensitive, or cameras that have filters that are sensitive for different types of light? You can play with these on Earth as well. For example, we have cameras specific for infrared, where you see actually the temperature of bodies. We have cameras that only filter out the X-rays to, for example, look at the bones inside our bodies. So what if we do the same trick on space missions? And this is what started with the first orbiting solar observatories, so orbiting the Earth, called OSO. And the first ones were launched by NASA. So these solar observatories were 8 in total, so a series of 8 spacecraft that got launched between 62 and 75. And these indeed, as expected, gave us the first observations of X-rays and gamma rays, particularly in flares. So in the solar flares, the places where we see most of the energetic radiation coming out of the sun. But they had very low resolution, and it was difficult to learn more than that. So a big game changer was Skylab. Skylab was the first manned space station that NASA built in '73. And so from time to time, astronauts would man the space station, and they would also operate 8 different solar instruments that were connected on a boom that was sticking out of the spacecraft, the Apollo telescope mount. And so they operated the instruments, and then they returned the film home to Earth to then get the images down. And this is one of the images that Skylab took. So what do we see here? We see the sun in X-rays and extreme ultraviolet. And you see indeed these, what we call active regions now, which are the hottest parts of the solar atmosphere. And these also happen to be located exactly on top of the sunspots we could already see from Earth. So it's very clear that the sunspots also mark the regions where the sun has most activity. What you can also see here are coronal holes. These are areas where suddenly the corona looks darker, and these are typically close to the poles. And in this particular image, you also see a very nice prominence eruption. So this is a prominence, as we have seen it before, that becomes unstable and is really getting bigger and bigger and bigger, and will lose some of its material later. This losing of material got really seen then by the next mission, launched in 1980, which was Solar Maximum mission. And this showed a very nice observation of what we call a coronal mass ejection, or a CME. So a CME is actually, you see here some kind of coronagraph type instrument, which means that you make an artificial eclipse. So you have an instrument that has a shield to shield the light of the photosphere, of the disk of the sun, so that you can see the outer layers of the corona in a better brightness. So here you see a sudden release of material, a bit like the image you saw before, but now it's really escaping. So this bubble is growing in the different images here, and so it's being launched into space. So this coronal mass ejection is also a sudden release of energy from the sun, a bit like a flare, but in this time it's a release of coronal material. And this typically comes also from an active region, or it comes from a prominence that we saw before in the previous image. So with these three missions really shedding a lot of new light on the sun and on the solar activity, this started a series of a whole series of new missions ranging from the 80s until today. So you see here a list of different missions that are all serving solar physics or the effects of the sun on Earth. And the list is even not complete. Now, these missions are all launched by different space agencies, often also different countries involved. So today I'm not going to go through all of them, of course. I will concentrate mainly on the big game changers and also on the missions where ESA was involved, which are the ones in blue. You see that many of the missions are still active today. So these are the ones that end here in 2020 and are still ongoing. So let's start with the first one here on the list, which was Ulysses, and which was very important because it gave us a lot of new material to think about. So Ulysses was a mission, a joint mission by ESA and NASA that got launched in 1990. And one of the reasons it got launched was to measure the solar wind. And the solar wind is a continuous stream of plasma, so solar material, that is escaping from the sun. So we knew this wind had to exist. We already felt it or measured it closer to Earth, but we wanted to know how the wind would vary if you fly over the poles of the sun. So all the planets rotate around the sun in the same plane, which is the ecliptic plane. And so this spacecraft wanted to escape that ecliptic and wanted to fly over the poles. Now, you can't just launch a spacecraft and then give it enough thrust or energy to actually bring it in whatever orbit you like. There's just not enough energy you can give or fuel you can give with the spacecraft to make that happen. So what you typically do is you use gravitational swings by other bodies and typically planets. So you could, for example, use the gravitational pull of the Earth or Venus or Mercury to bring your spacecraft into another orbit. In order to get to a polar orbit, however, this spacecraft Ulysses had to fly all the way to Jupiter to then use the big gravitation of Jupiter to bring it into this very special orbit. And then it did 3 orbits over the poles. So it saw the North and the South Pole 3 times. So what did it find? First, it found that there were different types of solar wind. So here on the left, you see the first orbit. And what you see here is you see the sun, how it looked at the time during the first orbit. So it was relatively quiet. There were not that many active regions or not very energetic active regions. And the spacecraft was flying over those 2 poles. So what you see here in the graph, in the blue and the red, is the solar wind speed. So you see, when the spacecraft was flying close to the equator, you had lots of variation in the wind speed. And then suddenly it got much more constant, but also much higher. So this is what we nowadays call the fast wind. And so the fast wind came out of this polar region here. Then the spacecraft moved closer to the equator again, saw the same thing happening, a lot of variation, slower wind, and then moved into the fast wind of the South Pole. Now, the second time, it did the same orbit. Now, suddenly, the sun was much more active. It had moved into a solar maximum, and the measurements were completely different. So here you see that now you have all kinds of solar wind speeds all around the sun. So this was a very, very important new result. First, that there were two types of wind, fast and slow, but that you could only really distinguish between the two during solar minimum, because during solar maximum, the wind speed is really varying a lot and very chaotic. So the next mission I want to talk about is a very important one, because this was really a big game changer in the field of solar physics, and that was Soho. And Soho stands for Solar and Heliospheric Observatory. It was a spacecraft built in Europe and launched by NASA in December 95. It was operated from NASA Goddard Space Flight Center, and I shouldn't say was operated actually, because it's still running. So it was designed for 2 years, and it's still running after more than 25 years now. Soho is not a spacecraft that is orbiting the Earth, but it is located in a funny point, which we call Lagrangian 1. So around in the system of Sun and the Earth, you have different points that have very specific, very special characteristics. And L1 is one of them. So this is the point which has equal gravitational pull from the Sun as from the Earth. So if you're here, you're kind of hanging there in space and you don't go anywhere. So you don't start orbiting, for example, the Sun. This is because the gravitation is the same from both bodies. So this is a very interesting point to launch a spacecraft to, because once they are there, they don't need a lot of fuel, or they don't need a lot of effort to actually stay there. And the good thing about L1 is that you have a very nice view on the Sun, and it's the same view as you would have from Earth. So this is where Soho is, and it has 12 different instruments on board. And why is that? Why so many? Well, Soho has had many different science objectives. So on one hand, it wanted to learn about the solar interior. We didn't really know much about what was happening inside the Sun, except that there must be nuclear fusion. But so the structure and the dynamics inside was not really known. Then we wanted to learn more about the solar corona. Why does it exist? Why is it so hot? Because it's so far away from the core. And then third, the solar wind. We saw the funny velocities of the solar wind. We saw that also the velocity was not constant. It was accelerated somewhere, and we did not know where and how. So in order to address those questions, Soho had different ways of addressing those. On one hand, it wanted to take continuous observations. So that's why we call it an observatory. It's really continuously taking imagery and other measurements with all the instruments. And the instruments are very complete. So it has 12 instruments on board to be able to study the Sun in all its different wavelengths, and also with many different techniques. So we have continuous UV imaging and spectroscopy, imaging of the solar corona, measurements of surface motions, the magnetic field on the surface, solar wind composition, energetic particles, and also the total sum of all the radiation that the Sun is emitting. So, what are the highlights of Soho? What did we get back from that mission? I think the most important one, the first one, was really the fascination for the sun, the beauty of the solar corona. So on the left side, you see a Soho movie taken in helium-2. That is a line which is a little bit hotter than the chromosphere we saw before. And so you see here prominence eruptions, you see them building up, you see them erupting, you see the active regions, and so you see the activity of the solar corona. The second part here, you see the same instrument, but now with a different filter, observing the corona in a hotter temperature. So this is about 1 million degrees. So you see the same type of active regions now, and you see flares happening from time to time. And so you see the hottest parts of the solar corona. The second thing that Soho taught us was we started understanding the magnetic field of the sun much better. We knew already that where sunspots appear and where you see those loops going from one place to another, you have some kind of magnet underneath. So you have a sunspot with typically one magnetic polarity, and then you have another sunspot with the other magnetic polarity. And this is where the field lines, the magnetic field lines form, and so the material is kind of caught, is trapped in these field lines. So through Soho, people started observing sunspots in much better resolution and much better time resolution as well. They started modeling them. They started understanding better the flows below a sunspot and how it's actually being created and evolves. So also the solar magnetic field in total, we understood better that actually it's this kind of complex magnetic field, at least at solar maximum, where you have some magnetic field lines sticking out from the top and the bottom, so close to the polar regions, and then you have all those loops forming the coronal loops closer to the equator. And that was also the reason why the wind here is slower and much more varying, as Ulysses saw. We also started understanding better how the solar activity in the magnetic field changed over the solar cycle. Because in the end, you have a body which is rotating differently at the equator as on the poles. But it's a magnetic body with all the material confined by these magnetic fields. So if you start rotating it differentially, then the magnetic field is dragged with it and it's kind of wrapping around the whole sphere. And then at the same time, you have bubbles of material popping up from down in the interior and coming up. And this is what creates those sunspot regions and those active regions later. And the good thing about Soho in particular was that, especially up to now, we have already seen 2 full solar cycles with the same instrumentation. And this is the type of thing that no other mission has done before. So this is just a movie to give you some nice views on the difference in the sun between solar minimum and solar maximum. These are not Soho images, actually. It is already a newer telescope, a newer observatory taking over, which has been launched by NASA. So here you see indeed the magnetic field lines both in minimum as in maximum. And the hottest corona here, where you see a lot of those coronal holes in solar minimum, and in solar maximum you hardly see them actually over the poles. A third highlight I want to address is space weather. And space weather is kind of a new concept since Soho. So Soho has coronagraphs on board. Let me go back to the beginning to explain it a bit better. And a coronagraph is this artificial eclipse. So here you see an image of one of the instruments on board Soho that shows you the corona. And these blue images here, those 2 are taken by 2 other instruments, which are both coronagraphs. And so they show you what's happening around the sun. Now, you see here a series of a few weeks in 2003, close to solar maximum, when there was a lot of solar activity. So you see CMEs leaving the sun, but since Soho and this instrument, we also appreciate what's happening around the sun, if that happens. So first, those clouds of plasma are really flying far away, and they are really affecting the whole solar system. What you see here, all those pickles here, is actually damage on the detectors of the instrument. So you see that the material that's being spat out by these CMEs is damaging the cameras of Soho. And it's also since these kind of movies that we understood better that we have to keep a close watch and see how Earth could be affected by these events. So we knew already about the solar wind, which is continuously streaming towards Earth. And here's Earth in this picture, and here's the sun. Well, this is an artist's impression, of course. It's not a real picture. You see the Earth being protected by its own magnetic field. And so the magnetic field is kind of pushed away by the solar wind, which is streaming continuously out of the sun. So you see here this bubble, which we call the magnetosphere, which is protecting the Earth. But then from time to time, you have a coronal mass ejection, which is some kind of solar storm. It's a large cloud of these electrically charged particles that suddenly escapes into space. So if this large cloud propagates in the direction of the Earth, it can really change this magnetic field, and it can affect Earth itself. Here's a slide with some of the effects. I'm not going to mention them all, but you have radiation effects, for example, and especially for astronauts, because they don't really live within the protective bubble of the atmosphere of the Earth. Also, spacecraft can have damage because of radiation, as we saw in Soho. And planes, also people on planes, can get extra radiation. Then you have changes in the upper atmosphere, especially the ionosphere in the Earth, which means that suddenly satellites are dragged, so are moving slower through the atmosphere, which causes navigation errors and also problems with radio communication. You have magnetically induced effects, so for example, overload on power networks and pipeline corrosion. And you also have a very beautiful effect, which is the aurora that you typically see over the poles of the Earth. All these effects are being induced by space weather. And since we are these days much more vulnerable to technological problems, because we have all our high-tech systems working on Earth, this is getting more important for humankind. So since Soho, we have really space weather observations. It's a little bit like a weather satellite that's orbiting the Earth, and it's looking at weather patterns or measuring wind all around the Earth. Soho has been our first way of keeping an eye on what the sun is doing and keeping an eye on the weather that is actually coming from the sun. And not only the observations were important, but because of the observations, scientists could start simulations, like the very complicated simulations you see here on what's happening on the sun, how the plasma could escape, and how then this cloud is moving through the solar wind. And so these days we have really forecast centers. We have centers also within ESA that are forecasting solar weather. Another spacecraft which got launched in 2006 and that helped a lot in this was a NASA spacecraft, which, well, two spacecraft actually, called Stereo. And Stereo, as the name says, wanted to look at the sun in stereo view. So from two different spacecraft that would have a different view on the same body on the same sun. Because of course, if you see a CME leaving the sun, it's not always clear to find out, is it moving towards us? Is it moving away from us? How fast is it? Because you have all those projection effects. Now, the stereo mission had a very smart design. Well, it has a very smart design because it's still flying. It wanted to launch 2 spacecraft in the same orbit as the Earth is flying, but one slightly ahead of Earth, so a little bit closer to the Sun so that it would move faster, and another one that would be behind the Earth, so it would move slower. So as time progresses, one spacecraft would slowly move ahead of Earth, and here you see the years when that happened, and the other spacecraft would lag behind. So in February 2011, they were at opposite sides of the Sun with the Earth in quadrature, so we could see actually Sun from 3 different sides. Then in 2015, they passed at the backside of the Sun. But then unfortunately, when they came back, we lost communication with one of the spacecraft. And so the other one, which is stereo A, did a whole round, almost a whole circle, and is now actually here. And we still use stereo A, to do stereoscopic observations from Earth and from stereo. There were also some new satellites that were orbiting Earth in 2009 and 2010. So in 2009, ESA launched a very small spacecraft, and it's actually more a technological mission, Proba 2, that wanted to try out, okay, can we do the same kind of solar observations, but with instruments and a spacecraft that is much smaller, that consumes much less power, and that has high autonomy, so that you have less cost, less maintenance, less operations needed to actually have continuous observations of the Sun. And it is flying around Earth in close to the day-night line. So it can continuously watch the Sun, and it's only as big as a washing machine. So it's really a very small spacecraft. So this technology experiment was a big success. So it got launched in 2009, and it's still flying now. And today it is ESA's space weather watchdog. Now, there was also a much bigger mission launched by NASA in 2010, and that was SDO, Solar Dynamics Observatory, that is taking over many of the things that Soho was doing before, measuring the Sun continuously, every day, very high resolution in many different wavelengths. There's only one thing it misses that Soho still has, and that's why we keep Soho alive, and that it is the coronagraph. We can't see CMEs flying out from the Sun with SDO. Okay, so where are we now with all those spacecraft flying in space? Well, we have the Sun and Earth here being protected by its magnetic field. We have several spacecraft orbiting the Earth that keeping an eye on first keeping an eye on the Sun and also measuring the effects of the Sun on Earth. We have cluster. These are 4 spacecraft flying around in the whole magnetosphere, also watching out for changes, for effects of solar weather. Then we have in the L1 point, we have Soho still looking for CMEs, and we have two spacecraft measuring the solar wind. We have stereo A here at the side, watching at the side to the Sun. So do we know it all now? Do we have everything in place? Well, not really. Because as typical in science, whenever you understand something better, whenever you get a new discovery, then you have a whole series of new questions that pop up at the same time. So we still have many questions remaining. What are some of those questions? What we don't understand really is we measure the solar wind close to Earth and what it is doing to Earth. But we don't really know, okay, how does the solar wind look like close to the Sun? And how does it evolve between the time it has left the sun and the time it arrives at Earth? Also, those coronal mass ejections and energetic particles, what kind of evolutions have they made between leaving the sun and coming to Earth? And in order to answer that, we want to really explore the solar wind from close by, and not only close by, but kind of explore the whole region between close to the sun and far out, which is close to the Earth. How can we really link effects that we see on the Earth to their source regions on the sun? Often they have already changed so much because of the distance and the solar wind that it's difficult to really link them. So how can we link them and better predict them? For that, we also want to go close to the sun to link cause and effect. We want to, if possible, fly through a CME, measure solar activity when it has only just left the sun. And then, last but not least, the magnetic field is creating all the activity on the sun. But how is the magnetic field itself created? We do understand some of it already, and we do have models, but we can't really predict why is this cycle exactly 11 years long, and also why is one cycle not the same as the next one. And for that, we need to find out what's happening at the one blind spot we still have on the sun. And these are the solar poles. We have never ever seen them. We have measured them through Ulysses, well, the wind coming out, but we have never seen the magnetic field at the solar poles or UV emission from the solar poles. And this is something that we are really missing still. So we would like to add 2 spacecraft to this nice picture already. One of them is Solar Orbiter, and the next one is its companion, Parker Solar Probe. So let's go to Solar Orbiter. So Solar Orbiter is a joint ESA-NASA mission. It has been built mainly by ESA, and it has been launched by NASA on the 10th of February this year. And its main goal is to explore the Sun heliosphere connection. So it wants to explore the solar wind, both from close by as close to the Earth. It wants to link the solar activity as we see it happening on the Sun with what we measure at a satellite. So we want to take cameras, and on the other hand, also sensors that measure the solar wind around the spacecraft. And then we want to go and observe the solar poles with cameras, with telescopes, for the very first time. So how will we do that? In this movie, actually, you see many different aspects of the mission at once. So this is the spacecraft being launched in its very compact configuration. And then after launch, you start extending all the extra equipment you need. The solar panels, for example, the antenna, and the heat shield is at the front, so at the sun side, the sun side of the spacecraft. The spacecraft is stabilized, so it can look at the sun all the time in very good resolution. And here you see the 6 cameras we have on board, using many different wavelengths. Some of those cameras have many different telescopes as well. And so they will observe the sun in many different ways. Something seems to be happening. Okay. These are the sensors that will measure the solar wind. And we also have a lot of sensors that are mounted on a boom in the shade of the spacecraft, in the shadow of the spacecraft. Then we will use gravity assist maneuvers by Venus to bring Solar Orbiter into its scientific orbit. And a scientific orbit is a highly elliptical orbit. So you see here Venus and Earth, and then you see the launch of the spacecraft in light blue. And so we launched it into a very elliptical orbit. So at times it's closer than Mercury to the Sun, and at times it's as far as the Earth. And then we use more gravity assist maneuvers by Venus, so flybys, to slowly incline the orbit out of the ecliptic, so that towards the end of the mission, we can see both solar poles. Now we have many instruments on board, and those instruments can gather an awful lot of data. So we can't have them all working at high speed all the time. So there will be times that we concentrate the telescope observations on. This is the closest place to the sun, closest distance, and also when we see the poles. Now the sun has a lot of very strong radiation, of course, so we have to protect the spacecraft with a specifically designed heat shield, which you can see here. So this is the body of the spacecraft where the instruments are mounted on. And then we have many different layers of heat shield. And the layers are also they leave space in between different layers, so that we can take advantage that heat can leave the spacecraft or leave the heat shield before it enters the spacecraft body. Now, of course, we have telescopes, so we also have to make sure they can observe the sun, so that's why we have those little doors. So in the front, the spacecraft will face 500 degrees, while at the back side, it will be minus 100 at the same time. And the spacecraft is only about 2.5 to 3 meters wide. These are the solar panels that can rotate so that we can adjust how much heat they can take depending on the distance. And these are the little sliding doors to give the telescope the opportunity to observe the sun. This is the antenna that will communicate the data with Earth. So Solar Orbiter today is still flying towards that scientific orbit. But we did have first light already, which means that we did test out all the telescopes, all the sensors, and we already came very close to the sun. So in June 2020, we were already at half the distance between sun and Earth, and we took these very nice pictures at that time. So you see here the full sun imager in EUV in 2 different wavelengths, 1 million degree corona again, and the 40,000 degree low corona. And then you see the high resolution telescopes that can only see a part of the sun, but in very high resolution and much precision. And there were already some new features seen in those images. And also we have 2 different wavelengths for the high resolution telescope. This is the magnetic field being measured by another high resolution instrument. There is not much to see yet because we are currently in solar minimum, no sunspots to see on that day. And this is the first test with the coronagraph we have on board. If you want to know where Solar Orbiter is heading and where it is today, you can look at this link here. Because it's heading kind of in all different places. This is maybe a little bit of a weird plot. But what we do here, you don't see the normal elliptical orbits around the sun, but in this plot we fix the Earth and we fix the sun. So normally the Earth is moving around, of course, and then the spacecraft is also moving around. If you fix the Earth, then you see where the spacecraft goes with respect to the space between Earth and sun. And then you see that actually Solar Orbiter is going kind of everywhere in this plot. So you see at times we are very close to the sun and at times we are very far. In 1 year we do about this shape. So we go to the far side of the sun and back to the Earth. And so we are often very, very far, much further than any other solar mission has gone. We go to the complete opposite side, and so to 2 AU away from Earth. We have changing distances from the sun, which is difficult for the instrumentation. And so we take different observations at each opportunity. We will not do the same thing every day, like Soho and SDO do, but we have really different opportunities for different signs. And we sometimes have difficulties to bring the data back. So we have an onboard memory to store it. And so sometimes data is stuck for up to 3 to 6 months. Solar Orbiter is also all about coordination. We want to have all the instruments working together. So we need to coordinate between the cameras and the sensors that are measuring the solar wind. Between the other solar observatories viewing the sun from different angles, like stereo, and also like SDO and Proba2 and everything that's looking from the Earth side. We also want to coordinate between observatories sensing the solar wind from different distances. For example, Parker Solar Probe got launched by NASA in 2018 and goes even closer to the sun. And then between different space agencies and ground observatories. I don't have much time to go into this, just quickly to say the differences between Solar Probe and Solar Orbiter. That Solar Probe goes even much closer to the sun than Orbiter, but because it's so close, it can't take cameras anymore. You can't look at the sun from that close by. So that's why the combination of those two spacecraft will be really interesting to find out more about the sun itself and also the solar wind. I suppose this is to remind me it's almost time. I'm not sure.
Yes.
Okay. I have, I think, two or three slides left. Is that okay, or shall I wrap up?
No, it's okay. Yeah.
Yeah, I will quickly go over some operations because that's the job I do. So in Solar Orbiter, the spacecraft was built in the UK, and ESTEC, which is ESA Center in the Netherlands, was managing that. The instruments were built by many different institutes all over Europe. Then all instrument commanding comes from those institutes to ESAC in Madrid, where I work. Then we send all those commands after they have been coordinated to Germany, ESOC, and they will add the spacecraft commanding and send it all to the spacecraft through antennas in Spain, Australia, and Argentina. So you really have many people involved. And these are just a few slides still with what is going to come. So I will go quickly over those because the future looks bright and sunny because we are already preparing for more. We have a new technology mission trying out a very special type of chronograph, which is made by two different spacecraft that have to fly in formation and have to keep the attitude of the two correct up to a few millimeters. So this is going to be really challenging. Then we will have a NASA mission coming up that will follow CMEs all the way from the sun, all the way to Earth. And we have a space weather mission by ESA, which is called Lagrange, and that will take over Proba2 and will look at the sun from the side where stereo roughly is now. So is there any future for Earth observations with all these space missions? Yes, also on Earth, we have complementary projects. This is the newest one, a very big telescope, 4 meters mirror that has been built in Hawaii. Because also on Earth, you can still do very interesting solar observations. And you have different challenges and different opportunities than in space, of course. And I want to end by saying that even today, with all our technology, we also still do sunspot drawing by hand. And you could think, okay, why in the hell would you like to do that? And the reason is you want to keep sunspot counting. You want to keep doing it in the same way to be able to compare sunspots today with sunspots hundreds of years ago. And you can only do that if you use the same techniques. So even today, we still have people drawing sunspots on a piece of paper. And I think this is a nice time to stop. So stay tuned for much more results to come from the sun because we have many different projects going on.